Hey folks, I'm going to solve a couple problems involving orbital motion, so circular motion and gravity combined. First one I would regard as like an essential problem. The second one is kind of more of a curiosity, so you are welcome to tune out after the first example or watch the whole thing. Here's our first problem. Shuttle orbits the Earth. We're going to use the mass of m sub e for the mass of the Earth. It orbits the Earth at a distance h from the Earth's center while maintaining a speed v. In terms of v, what speed would be required to maintain an orbit of 1.5 h? So what we have in our problem, and I'm just going to draw kind of like a partial view here, is here's Earth, and I'm going to draw a very goofy, like there's our satellite, and the satellite is orbiting at a certain distance. And so, you know, the satellite's going to travel around that circle. The distance between the center of the Earth and the satellite is given as h. And so that's like the combined distance between the center of the Earth and the satellite. So just remember that tends to come up like once in the AP exam, where you need to understand that for things orbiting planets and for things experiencing gravity of other planets, it's the combined distance of the radius of the planet and its height above the surface. In other words, you have to measure it from the center of the planet to the satellite. So basically, we need to figure out, you know, how the speed of orbit relates to the mass of the Earth, the height above the Earth's center. So, you know, as far as this goes, the satellite stays in orbit because of the force of gravity. That's more or less the essential idea, is that the reason objects have an orbit is because their speed kind of keeps the force of gravity in check, where the force of gravity is always accelerating them toward the planet, but their speed gives them enough, essentially, inertia to keep from falling toward the planet, and not so much inertia that it flies away from the planet. So we're going to start kind of where we always start, Newton's second law. And so this is going to be centripetal motion, or centripetal net force and centripetal acceleration, because the satellite's moving in a circle. The net force on the satellite is the force of gravity. So I will use G times me times the mass of the satellite. And then I am very specifically going to use h, so h squared, because this is essentially the same thing as r. And so I'm just going to use h from the get-go. That's equal to the mass of the satellite times the speed of the satellite squared divided by, again, h. And so, you know, the r in the universal gravitation equation and the r in centripetal acceleration are the same thing in these problems. And that will continue to be the case, where the distance for gravity is also the distance that you use for the circle for centripetal acceleration. And so we have some things happen. The mass of the satellite cancels. So we have one concept show up right away, that the orbit of a satellite doesn't depend on the mass of the satellite. So there we go. And then one of the h's cancel. You can imagine, like, you can multiply both sides by h, divide both sides by little m, and you have your equation. Now this will simplify. You'll notice there's nothing left over on the v squared side. The question is about v. So just to kind of backtrack there, the question says in terms of v. And so this is another proportional reasoning question. And so what you want to do whenever you see that is identify what variable your equation should be solved for. And in this situation, it's v, because your answer needs to be in terms of v. So we're looking for a speed, so we want to solve the equation for speed as if we were solving a numerical problem. So I'm going to solve it for v. I'm going to take the square root of v squared. That gives me v equals. And then I have the square root of all of this. And so I have g me over h and the square root of that. You will notice that, you know, when we covered gravity, we talked about the value of little g on a planet being gm over r squared. And so it's notably different here where we have a square root symbol and we only have an r instead of an r squared. So the equations can look very similar. By the way, this is the equation that I'm talking about. So don't confuse these two as the same equation. This one is the surface gravity of a planet. This one is the speed of orbit. So we'll just get rid of that one. Okay, so this is the equation that I'm working with, and it represents the first sentence in the problem. The shuttle orbits the Earth at a distance h from the Earth's center, and it maintains a speed v. So this is the before picture. And then to actually solve the question, we want to identify the after picture. So I'm going to prime my variable, so v prime. This will eventually be what my answer is, whatever the value of this is in terms of v. And I'm going to take this equation and identify any changes that I'm going to make. So, the value of big G doesn't change. The value of the mass of the Earth doesn't change. But what does change is the value of h is going to become 1.5h. So in the realm of things, this is not super complicated, but it's a derivation in order to do it. So, this equation is Newton's second law. You have the universal gravitation equation, you have centripetal acceleration. A lot happened between this line and this line. The net force is due to gravity, the acceleration is v squared over r, and then after we get here, we cancel some variables. So this is a derived equation. Not a bad idea to memorize this, but also something that, after this problem and maybe a couple other practice problems, you could derive this equation. And so this represents the speed required for a satellite to maintain an orbit around a planet of mass m and at a distance of h from its center. Anyway, back to the problem. V prime, my new velocity, is equal to all of this. And so just like I've done with the other proportional reasoning problems, I'm going to take the number out of the equation. So this is a little bit more complicated because I have 1.5 in the denominator and in a square root symbol. And so what I'm going to do is take 1 over 1.5 out in the square root symbol. So, I didn't actually do the math yet, but I just took root 1.5 out of the denominator and moved it over. And then what's left is root g me over h. So I have this, it's kind of a messy looking equation, but there's a point to it. Because square root g me over h is equal to my initial velocity. And so I get to say v prime equals v over root 1.5. So that would normally be a good enough answer, but I know you probably want to calculate it and get an actual number without a radical in the denominator because you're a good math student. So let's do that. If I do 1 over square root of 1.5, it's equal to 0.82 v. And so, what's the lesson in here? I increased the orbital radius by 50%, which means the speed actually has to decrease by 18% in this situation. So, because of the square root relationship, drastic changes in height are muted when you talk about the changes in speed. So there's your first problem. Okay, second problem is just more lengthy. So again, feel free to tune out now. We're probably going to be about 10 more minutes here for this one. And it's not essential. I just think it's interesting. So we have a spy satellite. And this is just one of the things about this problem is that it presents things in a very different way. The question is, what is the height of the orbit above the Earth? And you're left to put it in terms of essentially the mass of the Earth and the radius of the Earth. And you only get this fact that it orbits the Earth twice a day. So we can kind of approach this the same way we did the last one. and say, let's just use Newton's second law, because that's the only thing we've ever used for satellite motion, and the only thing that you really should use at this point in the course. Okay, and we're going to do like a lot of the same things. So I'm going to just go through this quickly, right? We have the force of gravity on the satellite is equal to this. Oh, sorry. I'm gonna erase this and start the video in a minute. Okay, that was probably a little bit of a jolt and something just got erased, but I put in the wrong variable in this situation. So I'm just going to put in a generic R for this. The reason is, right, if here's the Earth and here's the satellite, we have this shape orbit, and I have the same measurement, but the question is asking what is the height above the Earth, and you know, this whole line represents the R that I want to use. Sorry, this is very small writing. So we're going to say that like the R is the entire measurement. That's a combination of the height above the planet and the planet's radius. And so I'm going to have to like work with this. This is the one thing that makes this problem complicated, is that I have to understand that the question is not actually asking for the distance between the center of the Earth and the center of the satellite. It's asking the distance between the top of the surface of the Earth and the satellite itself. So that's a little adjustment. So I'm just going to put in an R to represent that entire distance, and I'm going to work with that. So, okay, I've done that, and I can do all the same canceling I just did, because this is, so far, the same problem. And I get this equation of GME over R equals V squared. Okay, so here's where like the rest of circular motion comes into play. The data I do get the mass of the Earth, and I do get the radius of the Earth to incorporate here, but I don't get the speed. And so what I want to remember is I get this fact about the satellite orbits the Earth twice a day. What that means, if it goes around the world twice every day, it has a period of 12 hours. And so I'm going to just recognize that that's part of the problem and say, oh, well, one thing I can do is, well, the speed of the satellite's a linear speed around the Earth. Speed is equal to 2 pi r over t. So r is something I have in my equation already, and then t is new. And so I can just do a substitution here and work with this. So it gets really messy right here. So GME over R equals, and then I have V squared. So I'm going to, if I want V squared, I have to square all of that. So I get 4 pi squared R squared over T squared. And I mean, I can organize this if I want. I could solve it for R. So why don't I try to do that? So I'm going to, this is going to be a mess, but I'm going to multiply this by R over T squared. And I'm going to get GME T squared equals 4 pi squared R cubed. And then one more time, divide both, no, I don't want to do that. Divide both sides by 4 pi squared. And so what I'm going to have is R cubed equals GME T squared over 4 pi squared. And so I have an equation. It's not actually solved for R. I would have to do a cubed root of everything. And that's fine. But I have an expression for R in terms of these things. So I guess let me just do that. R is going to equal all of this it's going to equal the cube root of this, so that would be to the 1/3 power. So now I go back. Okay, the mass of the Earth is given to me, and the period is something that I figured out. Now the period is in hours, so I just have to do some quick multiplication. 12 hours times 60 will get me minutes, times 60 again will get me seconds. The period is 43,200 seconds. So I can now compute this value of R, and I forgot my calculator, so I'm going to go do that and finish this calculation. Okay, so now I just have to organize my info here. So this value of R is going to be 6.67 times 10 to the negative 11th. Forgive me for not using units. That's G, times the mass of the Earth, 5.98, times 10 to the 24th kilograms, times the period, that's 43,200 seconds. That's going to be squared, divided by 4 pi squared, and then all of that is going to be cube rooted. Okay, so let's see if I can do this successfully. So we'll do numerator first, 6.67 e negative 11 times 5.98 e 24 times 43,200 squared. That's the numerator. Divided by 4 times pi squared. All of that to the 1/3 power, and hopefully I get a number that is somewhat reasonable. My value of R is 2.66 times 10 to the 10 to the 7th meters. Now that is good news. That distance, remember, that represents the distance between the center of the Earth and the satellite, which means it really needs to be bigger than the radius of the Earth. So it is. Okay, so that's my value of R. That's the value of the big radius. This value of height, we'll call it height, H, is equal to the value of R I just got minus the radius of the Earth. So if I take 2.66 times 10 to the 7th and subtract 6.38 times 10 to the 6th, so notice that the radius of the Earth is an order of magnitude smaller. So this is not going to change. It's not going to look like it's changing a ton. My answer is 2.02 times 10 to the 7th meters. So that is the height above the Earth, and that is considerably far above the center of the Earth. Almost 10 times the distance from the Earth. Cool, and so that's that. So kind of like the meat of this problem is recognizing that this measurement that you're given twice a day is a measurement of period, and you can use that to infer the velocity. Even if you can't calculate it, you can represent the velocity using period and make it so that the only unknown is the distance there. And there we go.